Okay, let's get going. Hopefully the audio will work here. Let me go full screen. Full screen. There's a syllabus here, which you all can read. I'll go through some of the things on it as we go along. I just want to first call your attention to the grading. The majority of it is based on homeworks. Those will be due approximately every other week. So those constitute the majority of the grade. There's a final exam, as those of you who have been at Columbia for a while know. The final exam schedule doesn't become official until late in the semester, but for a QMSS class, I've never known it to deviate from the projected final exam schedule, and it's currently showing it to be the first Tuesday of exam week, which is in May, early May, because we're starting early this year. And then finally, the third component of it is like class participation. I've seen a number of you before. Some of you I've never heard speak. So I assume you can, but that may not be something that you're most comfortable doing. And so class participation also can be gained by asking questions, ideally giving answers, follow-up questions, etc. on Piazza, which I believe most of you are familiar with. And after class today, I'll set up the Piazza thing for this class. And then if you just go into Canvas and then click on Piazza here, if you haven't done it already, it'll ask you to a password, and that'll take you to this Piazza thing, which is basically a discussion board for classes like that. There's a ton of things that can and should be discussed in a class on Bayesian statistics, not all of which we'll have time to discuss thoroughly in class. And so being able to discuss those things, ask questions, etc., through Piazza outside of class is a really useful thing to be able to do. I will have office hours where you can further discuss stuff. Those, I believe, will be on Tuesday afternoons. You can sign up for a slot through Canvas. If Tuesday afternoon doesn't work for you, just post on Piazza. We can set up another time. So basically, you shouldn't really need to be emailing either me or the TAs, which we have two of. Terry Zhang back there and Rui Liu next down. They'll be grading and helping us out with homework, a bunch of other things. You cannot get too much help for a class like this. So with all that said, let's jump into it. Maybe some more people be showing up. Get some more size here. Okay, great. Lights. Good. Okay, so this is 5065 Bayesian statistics for the social sciences. I am Ben Goodrich. Probably should have started with that, but most of you all know who I am and what this class is anyway. This talked about a bit on the syllabus, but this course, like basically all QMSS courses, is going to use R as its primary computer language. It's basically the official statistical computing language of the QMSS. So if you have not used R before in a class, it's going to be pretty difficult because we're not really teaching the basics of R, because most QMSS students would have at least been using R last semester, if not before. If you haven't used R, but you have used another programming language such as Python, Java, things like that, you might be able to get by, but you're probably going to be sort of teaching yourself R at the same time you're trying to learn all this Bayesian statistics stuff. So that's ambitious, but it's been done before. If you're only familiar with you know, Stata or Excel, things like that, then this class is going to be basically impossible. Just because we're not going to have time to slow down and like guide you through just how to start R and how to load up a file and things like that. Homeworks have to be done using the R Markdown format. If you haven't done that before, we'll explain it, but it's basically a mixing of R code and, you know, English explanations of the output. It makes plots and things like that. That is not too difficult as long as you're previously familiar with R. We'll be using Stan as the semester goes on to actually do Bayesian analysis. Stan is yet another programming language which will access from R. So that that is going to be pretty simple for those of you who are comfortable with R. Stan is an open source project developed throughout the world, but primarily here at Columbia, where we have 5 or 6 people who are full-time. They don't teach, they just develop Stan. And so this is sort of an exciting place to be learning about Bayesian statistics because it's on the forefront of the software that can be used for that. Like I say, we'll be using it from R, but Stan, the library, the language, etc., can be accessed from a variety of other interfaces, Python, MATLAB, etc., that you may prefer to use for the Bayesian inference after the class is finished, and that's all fine. But we're going to be using the R interface exclusively, and you need to be using R for the homeworks, etc. Questions about that? Any Excel user want to get up and leave already? Any Excel user want to stay? Okay. So on the topic of Stan, Columbia makes me say this. I'm an employee, obviously. Columbia, having received several federal grants and stuff like that to develop Stan, gives rise to a problem because I also use Stan for some business purposes on the side. And according to Columbia University policy, which you can click on if you really want to read some mind-numbing legalese, in a situation like this, whatever, expected to earn at least $5,000 from some company that's not Columbia, required to disclose these facts every time you do a presentation. So be aware of that. No, seriously, we're doing this every Tuesday and Thursday for the whole semester. So make sure you show up on time. Don't want to miss the disclosure. All right, so the reading for this week, which I sent out an email for those of you who are officially registered. If you're not officially registered, that's fine for the time being. You should officially register at your earliest opportunity. SSOL was being like very weird over Christmas, not letting people put themselves on the wait list, whatever. So if you saw the email, it had links to the reading and the video historical background for today. If not, you know, you can catch up on that. But there's a book by a guy named Richard McElreath or McElreath. I've never been entirely sure how he pronounces his last name. He was the first person to write a textbook that was really based on Stan. It's called Rethinking Statistics, a Bayesian course with examples with R and Stan or something like that. And in the introductory chapter, sort of lays out his vision for how a class like this will go. We're not using this book in its entirety for this class this semester, but I think a lot of the philosophy is the same. And this book, it's in the QMSS office if you want to read more chapters from it. But anyway, Richard says statistics is neither mathematics nor a science, but rather a branch of engineering that gets used for science, in our case emphasizing social sciences. But advanced courses in statistics tend not to emphasize the engineering aspect of it. And most people, even in PhD programs, never get that far into it. And so teaching statistics in some ways resembles teaching engineering backwards, starting with how to build a bridge and then ending with, you know, basic physics about the, you know, durability of the materials and things like that. And that, unsurprisingly, can lead to serious trouble. Especially when scholars try to go on to do conducting innovative research beyond what your peers are doing without really having a good foundation in basic physics. It's like we got hydraulic engineers by promoting people who are good at plumbing. And so the sorts of things that are often taught, around Columbia, et cetera, he's referring to those as classical procedures, introductory statistics classes. They tend to be both inflexible and fragile. Inflexible in that when you go to do something that's a little bit innovative, there's very limited ways in which you can adapt them to these new situations, new sorts of data sets that are becoming available seemingly every week these days. And fragile, he means that they break in unpredictable ways. They break in ways that are not evident to the user when they're being applied outside the situation that they were developed to. And most of these things were developed in like the 1920s, when quantitative research was a very different thing back then. There wasn't even social science by any way in which we would recognize it today. And so they were intended to solve problems that are not really representative of the sorts of problems that we tend to see today. So the analog of basic physics for Richard, for us and for the people reading Richard's book, it's probability. And what do I mean by that? A shared language for communicating about uncertain propositions, maybe propositions in the future, but even propositions, in the past. Who shot Kennedy? Did they act alone? Like those sorts of things. They're in the past, but we're not entirely certain about all the details of them. Now, even though QMSS goes well beyond introductory classes, it doesn't explicitly offer or really even encourage people to take a class on probability theory, such as the classes that they offer in the statistics department. And there's good and bad reasons for that, but this is really the hardest aspect of a class like this, to sort of catch up the gaps that are in people's knowledge about probability, while at the same time using probability to do interesting stuff using quantitative methods for social science research. And in order to be Bayesian, even more than some of the other approaches to quantitative methods that we'll talk about, you have to know and you have to learn probability theory. And so we're going to get into that starting Thursday and spending a lot of the first part of the semester dealing with probability theory for random variables, learning distributions besides just the normal distribution, etc. And so that's really the biggest challenge that people have with a class like this, is that we're using this stuff in probability, and that ideally you would have taken like a semester, if not a year, on it before jumping into relatively advanced Bayesian stuff. And so we certainly can't spend that amount of time. We'll try to spend the minimum amount of time, but if we spend any more than that, we wouldn't really be getting to the good stuff, the cool stuff that we'll get to in April. So to be Bayesian, you have to know about probability theory, but that's not all. You have to know a good bit about computer programming, in our case with the emphasis on R and STAN. You have to know a good bit about the science, about the substance that you're trying to model. And so, people sometimes ask, well, if you have to know all this stuff, why aren't there sort of official prerequisites? But with QMSS being ostensibly a 1 year or maybe a year and a half program, you can't really have hard prerequisites. We can't really say, well, you should go back to your undergrad university and take stuff that you didn't take when you were there. Moreover, it's not like there's a single class that you could go take to be prepared for something like this. It's really 2 or 3 different classes in 2 or 3 different departments, maybe. So that definitely makes it difficult to do. And so you're not really prepared for a class like this, but we understand that you're not really prepared for a class like this. And sort of the sooner you get over that, the better you're going to do with a class like this. Finally, to be Bayesian, you have to be prepared for everybody, even other Bayesians, to disagree with you. It's not something for the meek, and you're sort of jumping into something that is contentious and taken a lot more seriously than perhaps you realize when you get started with it. But that's just, you know, kind of the way it is. So before we can talk about probability, we have to talk about classical propositional logic that was sort of credited to Aristotle, student of Plato, teacher of Alexander the Great, greatest Alexander of all time. Famous. And he famously came up with a system of logic that goes a little bit like this. You have your major premise, such as all men are mortal, your minor premise that Socrates is a man, and from those two things you can conclude that Socrates is mortal. And that was something that was not merely true in theory, but actually true in practice. Socrates is dead, unfortunately. But the logic that goes along with this lives today, and it's important for classes in logic and some things in computer science and things like that. But there's approximately 0 interesting applications of this sort of deductive thinking in the social sciences. And the closest thing that I can come up with is something that's referred to in political science as democratic peace theory, which goes a little bit like this. Major premise: no two democracies fight a war against each other. Pick any two countries, such as Canada and arguably the United States, that are democracies, and come to the conclusion that Canada and the United States will not fight a war against each other, which they haven't, at least not for several centuries. But whether this is as true as the Socrates thing depends on how you, as the social scientist, operationalize the word democracy, and how you operationalize the word war, and how you operationalize the word, you know, is, and things like that. And when you don't do so carefully, the literature can de-evolve quickly into things where we publish articles arguing whether or not the Falklands War is, you know, exception to this line of research, and it sort of hinges on pretty arbitrary distinctions, such as whether Argentina would be considered a democracy in 1982. No one at the time did, but political scientists, the way they code, you know, democracy scores, kind of found that Argentina had, you know, a few months there where it was a little bit less strong military rule. And then there's a question as whether the Falklands War was actually a war. Only about 900 people died, which is 100 people short of the traditional threshold that political scientists use to define a war over sort of the least strategic rock on the world, etc. It doesn't really have a lot of the characteristics that we would associate with like World War I or things like that. But it's basically a semantic question. And a better social scientific question, if you wanted to study this, would be to ask questions like, why is it the case that democracies are much less likely to fight a war against each other compared to wars involving one democracy and one autocracy, or wars involving two autocracies? So, you know, there perhaps have been like a single-digit number of wars between two democracies and like a ton of wars involving at least one autocracy. Why is that? That is a much better question, and hopefully one that IR people have been focusing on more since the last time I had to learn stuff like this. And probability is basically an extension of this idea of classical propositional logic, where the propositions are not just true false things like Socrates is a man, but rather stuff that is sort of possibly true to a greater or lesser degree. So to sort of stick with political science, literature is sort of consistently found, not just in the United States, but other places that have presidential systems, that the parties of unpopular presidents have a tendency to lose seats in Congress or Parliament, whatever, for the parliamentary elections. Trump is currently likely to remain fairly unpopular. Last I looked, he had sort of a 40% approval rating, which is actually not that low by U.S. presidential standards, but his disapproval rating is a lot higher, and people who disapprove of Trump seem to be sort of very committed to disapproving of him. And so if you put those two things together, you come to the conclusion that Republicans will probably lose seats in the 2018 elections, but none of 1, 2, or 3 is really like a logically true thing. It's just, a tendency or, something that has some evidence behind it, but it's not something that you can say guaranteed the Republicans are going to lose control of the Senate or something like that. However, 3 should seem plausible to someone, at least to some degree, if you accept both 1 and 2 as being true. Now, there's certainly among the 40% of people who approve of Trump's handling of the presidency, there's a lot of them that would, probably disagree with point 2 or maybe point 1, who knows. And so if you reject those, then 3 doesn't seem so plausible. But like Aristotelian logic, if you accept the first 2 things, then the third thing is true to some degree. Not necessarily absolutely true or absolutely false, but some gray area in the middle. And Bayesianism is basically a school of thought that uses probability to describe someone's degree of belief that a proposition is true, and to quantify our uncertainty about whether a proposition is true. And so if someone comes up with a forecast for how many seats the Democrats will have in the Senate, in 2019 or whatever, that forecast should come with uncertainty because the researcher in advance of that happening is not going to be absolutely sure that they're going to have 51, 52 seats, whatever it may be. So basically, probability theory from a Bayesian perspective is a weaker form of classical propositional logic, where you're not dealing with true or false, but rather with shades of gray between true and false. And true and false are just sort of extreme limiting cases where we really are pretty sure that this is true or false. Questions about that? No? All right. So we'll talk more about that as the semester goes along. I would say you could identify 4 sources of uncertainty when doing quantitative methods in the social sciences. We can have uncertainty about the parameters in a model. So what is the marginal propensity to consume in the United States? We can have uncertainty as to what that is, or if it's changing over time, what it's going to be in the future, after there's a major change in the tax legislation or something like that. So we can have uncertainty about parameters in a particular model. We can have uncertainty about, and we do have uncertainty about, which model that we might try for a particular data generating process is the best one, or which ones is better than others. The third thing, uncertainty about what to do with the output of the models, especially the best models or the best singular model. Once you have, the estimates and the implications of it, what do you do in order to make some decision or take some action as a result of the findings that this model has told you, with these estimates of the parameters? And all of those are sort of fundamental, I think, to science. There's a fourth source of uncertainty that we have when doing science with quantitative methods is uncertainty about whether the software that you're using works as intended. And that may seem pretty trivial to you, but it's not, particularly when you start to do innovative research, when you start to do things that are outside the scope of what the method was originally developed, again, maybe even before we had computers, to do. The software might not work as intended, and if it doesn't, it might not tell you. And so you have uncertainty about that. As I was saying, Bayesians use probability to describe their uncertainty about anything, particularly one, the parameters, and uncertainty about two, what models are best. Once you've sort of adopted the Bayesian approach, that basically dictates how you want to use the output in order to make a decision, ties into something called decision theory, which we'll talk about. But basically, once you have the output, you should know exactly what you want to do with it in order to make your conclusions or to make your decisions or your actions as a result of that. And that's one of the big advantages of the Bayesian approach compared to some other things that we'll talk about in a minute. The uncertainty about 4 really isn't integrated into 1, 2, and 3. But the STAN software that is being developed by me, other people at Columbia, other people around the world, does as much as we can to mitigate the uncertainty associated with the use of the STAN software. It has a high chance of working as intended, and when it doesn't, it ought to be pretty obvious for people who are experienced using the STAN software. So you may have heard about, other software, other approaches, and they kind of refer to probability. But I think in comparison to the Bayesian approach that we're going to learn about this semester, they fail to deal with one or more of the previous 4 things. And as a consequence, really understating the uncertainty that we have about things. And this appeared a little bit back in 2016 when Trump was elected president. There was, at the time, a lot of research by political scientists and others that was pretty confident in predicting there was a very high probability, like 96% or something like that, that Hillary Clinton would win. And that turned out to be wrong for a variety of reasons that we're not going to go into today. But part of it was the software and the ways in which political scientists, et cetera, were approaching the problem pretty substantially understated our uncertainty and understated the ways in which sort of patterns that happen in one state might, replicate themselves in other states that we thought Hillary Clinton would win, and it turned out that she lost. So part of that, a good part of that, could have been perhaps avoided if there had been more emphasis on Bayesian methods and more emphasis on using Bayesian methods correctly. But there are alternatives, and there's classes on each of these, and we'll talk about them briefly in the next few slides. A bunch, including so-called randomization inference, frequentist inference, supervised learning or data mining, thing called fiducial inference. There's others that sort of contrast themselves with Bayesian inference. And so what is randomization inference? If you really want to know, you should take one of several classes that are offered at Columbia about this. But anyway, in the 1920s, this guy named Fisher wrote a book about the design of experiments where he sort of codified these ideas for the first time. But anyway, it's a method of inference specifically designed for randomized experiments. And so in this, as related to the previous 4 things, there's basically only one parameter to estimate. That's the average treatment effect, but you're estimating it for the people who participate in your experiment without necessarily having any ability to generalize beyond the people or whatever the subjects are in your experiment. In this setup, there's not really a model, and a lot of people think this is an advantage of randomization inference, that you don't have to worry about your uncertainty between this model or that model, because there really is just sort of one non-model. And even though they didn't have computers at the time, the implementation of it is so simple that you know, is pretty easy for them to do. So if you take the 42 people who are officially enrolled, we look like we may have a few more than that. But the 42 people who are officially enrolled, and you wanted to assign 20 of them to treatment and 22 to control, it turns out there's over 500 billion ways which I could make 20 of you treatment and 22 of you into the control group. And the researcher randomly chooses one of them, or his or her computer chooses one of them, such as, you know, the 20 people here. They were chosen by at random by R from the list of people who are officially enrolled in the class yesterday. So if you're on this list, imagine you're, you know, get some pill, a new treatment. Hopefully you don't have any diseases that require treatment, but anyway, it's a pill that makes you smarter, ostensibly. And the other 22 of you and the people who are not officially enrolled, you're in the control group. So you just get a placebo. And then we're going to do this experiment. So having randomized who gets to be in treatment, who gets to be in control, I actually give you the pill or the placebo, come back like a year later, measure how smart you are in order to see if there's treatment effects for this particular pill. And the estimated average treatment effect is very simple to calculate. It's just the difference in the mean outcome between the people who are in the control group and the people who were, or people who are in the treatment group, people who were in the control group. And the reason why you can get away with such a simple estimator is because treatment assignment was randomized by me. And so it's known to be uncorrelated with any other background characteristics that you might have that would, you know, explain some of the variation in performance on a test or something like this. So at this point, you might think you're done, but you're not. You have to ask yourself the question, well, what would be the, after the experiment is over with, what would be the difference in means between any of the other 513,791,607,419 ways that there are to divide 42 people into one group of 20 and one group of 22. So all these other ways, you might anticipate that the difference in means between those groups would not be as big as in the one way of dividing you into 20 and 22 that actually corresponds to treatment and control groups. So if I just did like everybody over here is in group 1 and everybody over there is in group 2 and did the difference of means, some people in group 1 would have actually gotten the real pill and others would have gotten the placebo. And some people in group 2 would have gotten the real pill and others would have gotten the placebo. And so when you do a difference in means for something that's, you know, just this sort of left-right split into two groups, you might say, well, the expected difference in means should be about 0, as in contrast with the expected difference in means with the actual treatment group and the actual control group that were used in the experiment. That should have a much bigger difference if it's the case that the pill actually does something. But in the special case where the true treatment effect for each individual is actually 0, it has literally no effect on how smart you are or any other like side effects or anything like that, then these other, you know, 500 billion or whatever -1 ways to divide people into two groups and do their difference in means form a probability distribution. You can think of this just like a histogram. It's going to be centered on 0, but it's never going to be exactly 0. There's no way I can, you know, measure this and get two groups that have exactly the same mean. And that distribution can be compared in magnitude with the actual average treatment effect that you came up with for the one grouping into treatment and control that actually corresponded to the experiment. And the proportion of these half trillion things that yield a difference in means then is greater than the one difference in means that you calculated for the actual treatment and control group, is what Fisher originally devised as the p-value for the null hypothesis of no treatment effect. And that was the original usage of a p-value. But in that context, there really was no alternative hypothesis. There was just a null hypothesis. In this proportion of times that the half trillion difference in needs exceeds in magnitude the average treatment effect that you estimated, is just sort of a normalized measure of evidence against the null hypothesis that doesn't have like units or whatever. It's just in probability metric, which is considered to be unit free. But that's where the idea of a p-value originally came from, even though what you see in social science research today is, you know, different from that and is being applied in situations that are not experiments. So I don't want to get too bogged down in the details of how this works. But does anybody have any questions about the idea of randomization inference? The main thing about it is it's the researcher who does the randomization. The researcher's random choice into treatment and control is what gives rise to probability in the randomization inference framework. The other thing to keep in mind is this only pertains to the people in the experiment. Sort of the weakness of particularly lab experiments is they don't have any sort of quantifiable way to say how generalizable they might be to some broader population if you were to do the treatment in the broader population. So 1920s, same guy devised another method of inference, this time dealing with observational data. And here the goal is to make some inference about a population, in particular about a population parameter in a model from a relatively small but random and representative sample from that population. And this was devised because if you want to make inference about a population, particularly in the 1920s, it would be very expensive and time consuming for you to collect data on the entire population. But if you take a random sample, you can still make some progress, even though that random sample is much smaller than the sampling frame. So at the time, Fisher was in England. The British population was about 36 million. And if you wanted to do a survey, which Fisher wouldn't have done, but somebody might have, you could take a sample of like 500. And just the same way there's like 500 billion ways to make 42 of you into treatment and control groups, there's E, the irrational number, raised to the power of like 6,000 ways to take a sample of 500 from a population of 36 million. And we're going to use our sample of 500 to try to make inference about, the other 35 million plus people that were in the population, but not the sample. So the data collector, which may be the government or something like that, chooses one of those ways to pick 500 out of 36 million at random, collects the data, and then gives it to the analyst. So in randomized inference, it was actually the analyst who was doing the randomization into treatment and control. For most observational studies in the frequentist paradigm, maybe one person collects the data and they're responsible for doing the random sampling choice from the population into the sample, and then the data gets analyzed by somebody else, or maybe many other somebodies. And so you do the analysis, you might estimate average income, average height, whatever it may be, average age. And then you have to ask yourself the question, well, what about the other E to the 6,000 something minus 1 other ways that I could have taken a sample of size 500 from a population of 36 million? and I could have, calculated the mean on that sample, and I would have gotten something at least slightly different from the mean I obtained with my actual sample. I'm not going to actually do any more sampling because the whole reason for sampling in the first place is it's expensive, and I've already exhausted my budget just doing my study on 500 people. I'm not going to go out and get another 500 people. But you can imagine this sort of counterfactual world in which you might do something like that, and you might ask the question, how much should I expect my estimated mean to bounce around from one sample of 500 from this population to another sample of 500 from the same population? So I have multiple different, sometimes considerably different estimates for the same population parameter taken from different samples of 500 that randomly differ from each other due to the randomness of the sample inclusion mechanism. And the probability distribution of the sample mean estimator over the e to the 6,000 ways to draw a sample of 500 from a population of 36 million can actually be derived analytically, and you get this sort of distribution that you could use under some assumptions about what the mean and the variance and whatnot in the population is. And those assumptions are sort of codified into this way of doing hypothesis testing today. But that was influenced by other people, Jerzy Neyman, Egon Pearson, who in the 1930s devised another way of doing hypothesis testing where you have 2-point hypotheses. Like one hypothesis, this thing is 0. Another hypothesis, this thing is 0.25. And then you collect data and you see, whether you can reject one or, both or something like that of those hypotheses. Neyman and Pearson also popularized this idea of a confidence interval estimator. We'll talk about all those. But what is done today is sort of a combination of Fisher and Neyman that neither one of them explicitly endorsed, and neither one of them endorsed anything that the other did. They, basically worked in the same department for a little while, hated each other, and then Neyman moved from London to Berkeley in order to get as far away from Fisher as he could. But what is done today was sort of, like a halfway thing between these two basically incompatible approaches to hypothesis testing from a frequentist perspective. But they both had this idea about, can we use the information from one sample to, reject some hypothesis about a parameter in the population. So we'll get into more of that. And this is what Richard really thinks is the biggest problem with the students, PhD students in biology and other departments that he interacts with, is this tacit belief that the proper objective of statistical inferences is to test and to reject null hypotheses. This sort of goes by a philosophy of science guy named Karl Popper, but not really, because Popper, whether you agree with him or not, was talking about sort of testing substantive hypotheses, whereas all this null hypothesis stuff is about usually testing a hypothesis that you don't believe, like, this parameter is 0, rather than sort of testing, what you believe it actually is. And there's at least 2 reasons why Richard doesn't think that the proper objective should be to test and reject null hypotheses. One is that there's not a one-to-one relationship between hypotheses and models. Some hypothesis could be, evaluated with multiple models. And moreover, each of those multiple models is not going to be uniquely tailored to one hypothesis. You're going to have like multiple variables and stuff going on in them. And if, one of those is mismeasured or, has something else wrong with it, it could, cause you to think, one theory is true when the other theory is actually true, based on some other part of the model that, sort of comes along for the ride. So the lack of a one-to-one correspondence between hypotheses and models means we're not really in a good position to conclusively reject or, affirm some hypothesis on the basis of a model. And even if we could get around that problem, the fact that we have measurement error, particularly in the social science, prevents this sort of deductive Aristotelian, somewhat Popperish approach to, falsifying democratic peace theory because like Argentina and England fought a war for like 2 weeks over a place that had more sheep than people. Maybe there were actually 1,000 people killed that, we never find. We don't know exactly what the measurements are for a lot of these things. And measurement error could also lead to, deducing the wrong thing if you sort of take that approach. And the alternative that Richard is talking about and that we'll follow along in this class, even though we're not using the book, is that we need a set of principles for designing, building, refining statistical procedures that are as narrowly as possible tailored to the thing that we're trying to make a conclusion about. And all these other approaches to quantitative methods and sciences have some sort of a theory that builds binds these things together, but that's not really taught in introductory classes. And so there's a benefit in sort of going back to basics, which is really the way that I, prefer to teach, to really emphasize foundational stuff, concepts. And if you get those down pretty well, then you ought to be able to handle, the details on, the final exam and thereafter. And so the three main things that Richard thinks are important for this endeavor are Bayesian data analysis, which is the subject of this class, multi-level models, which are very natural in Bayesian data analysis. Indeed, it's pretty unnatural to not use a multi-level model if you're Bayesian, not so much if you're a frequentist, and to compare one model to another to quantify our uncertainty about which model is best using information theory, which is sort of a branch of communications that goes back a long way, 1940s and stuff, Shannon, all those people. Anyway, it's evolved today into something that's really useful for saying, what model is likely to predict better than another model. And so these are sort of the three building blocks on which he wrote the book and on which, we're teaching this class. Questions about, where we're coming from with all this, where we're going. Okay. So what is Bayesian inference? You might, whether you know it or not, or perhaps you at least should, have beliefs about how much the S&P 500, or loosely speaking, the stock market in the United States will grow by the end of 2018. Obviously, no one knows that for sure, but you might have some beliefs about how much it will grow. But your beliefs may be different from somebody else's beliefs. But let's say you have such beliefs and you express your beliefs using the language of a probability distribution. So for example, your beliefs about how much the S&P 500 will grow might be a normal distribution that has a mean of 5% growth over 2018 and a standard deviation of 3%. So that's basically conveying your belief. It's unlikely, albeit possible, that the S&P 500 will actually be lower at the end of 2018 than it was at the beginning of 2018. And there's about an equal chance that it'll be negative as there is a chance that it'll be above 10%, which would be, you know, not unheard of, but pretty optimistic, etc. But you might have some other distribution. You might have a normal distribution that has a different mean and a different standard deviation. You might, you know, have something that differs from what your parents believe or something like that. And that's all fine, because as more data comes in over the course of 2018, you and everybody else have an opportunity to update your beliefs about where the S&P 500 will be at the end of 2018 to some new probability distribution. Might be normal, might be not. But when it comes to like October, you ought to have a distribution for what the end will be in 2018 that has a standard deviation that's like smaller than 3%. That might be reasonable as of January, but as you get all this more information with the economy and stuff like that over, you know, the first 10 months of the year, by October you ought to be more sure what the S&P 500 is going to be at the end of December than you are today. And the process of updating your beliefs according to Bayes' rule is really the estimator of things. It's really an estimator of a probability distribution, and we want to learn how to do that. In this case, the data are not, and fortunately they need not be, a sample from some bigger population or an experiment that has been randomized. Like the macroeconomic data that's going to come over 2018 and about like the future and stuff like that is neither of those things. We're just saying, conditional on the data that we've received, how should we update our probability distributions that we use to describe our beliefs, and how can we do it in a rigorous, scientifically justified way? That's really what we want to learn over the course of the semester, and learn how to actually put that into practice various ways using the STAN software from R. And I'll skip the story, but we're going to come back to Bayesian inference basically every day for the rest of the semester, so you'll have a better idea of how things like that get put into practice. So there's another approach to quantitative methods in the social science. A number of you were in a data mining class in the fall where we talked about this ad nauseum. So suppose you have a data set of size n, and this also is typically not going to be an experiment. So nothing is being randomized, although in some cases it is. But in general, it's not an experiment, and nor is it a sample from any well-defined population. So none of Fisher's work applies to that situation. And so when you put something into Stata or whatever, and you get estimates, Stata is assuming for its estimated standard errors and confidence intervals and frequentist stuff like that, that the data that you loaded was a sample. Maybe not a simple random sample, but a representative sample nonetheless from some well-defined population. And all the stuff that comes in the output is telling you about, you know, how much these estimates would bounce around from one sample to the next, assuming the data that you fed it actually was a sample. Yeah, there's tons of people in the social sciences that are using these sort of frequentist things with data that in no way, shape, or form is a sample. So they have data on, like, you know, unemployment rate in the 50 states, and they feed that to Stata, and you get all these like confidence intervals as to how much the estimates for unemployment would bounce around in another sample from like 50 different states, ignoring the fact that there's only 50 states to start with. So if you have aggregate state level data from each of the 50 states, you have the population, and you don't have the problem that sampling was intended to overcome, which would be getting data for the whole population is too expensive. So you have to get data from a much smaller sample. But anything that you collect on states, if it's available for one state, it's usually available in the same place for the other 49 states. So there's no like huge cost to getting, you know, unemployment rates or whatever for each of the 50 states. You don't have to just like get 2 or 3 and call that a sample, because getting all 50 is pretty cheap. Anyway, those are the sorts of data sets that people in supervised learning are often using. They, you know, work at one of these tech companies like Yelp or whatever that just doesn't sample. It just absorbs data from everyone who logs into the Yelp website and posts a rating about, you know, some restaurant or whatever. Those restaurants were not random sample from the population of restaurants. The people who ate at them were not a random sample from people who ate at that restaurant. No one is excluded that's in the population but not in the sample. It's basically just getting as much data as it can on everybody, and then the task is how to analyze that. And if we're doing it with supervised learning, we want to like predict what, you know, how popular a restaurant is or something like that. One of the sort of received wisdom as to how to do that is to divide your original big data set of size capital N into 2 smaller data sets. One maybe like 75% is big, we'll call training data, that's little n. And the remaining, let's say 25%, is big N minus little n. So how many ways are there to divide a data set of size capital N, which may be in the millions or billions even, into training and testing? Well, it's n factorial, big N factorial divided by little n factorial divided by the difference between big N and little n factorial. It's just going to be a, you know, incomprehensibly large number, like even bigger than e raised to the power of 6,000 ways of doing that. The analyst randomly chooses one of them, chooses parameters to minimize some loss function over the training data, uses those estimated parameters, often without really looking at them, in order to predict the outcome in the n minus n observations that are held out for the testing data, and then compares the predictive accuracy in the testing data to when you do this process with a different model on the same data set split into 2 pieces the same way. And so supervised learning really focuses on this question, which model of the like hundreds that I could estimate is best at predicting this outcome in the held out testing data. Doesn't really quantify our uncertainty as to, you know, which one would be best in like future data, which is really what the, you know, CEO of Yelp is probably interested in. So it doesn't quantify uncertainty, but it does really focus on this idea what model is best. But you can and should ask about, well, what are the other ways, which is, you know, n factorial divided by little n factorial divided by the difference factorial less 1, other ways of dividing this big data set into 2 groups, training and testing, and that, you know, if you had a different split of the data, you could have come up with a different conclusion as to which model predicts best in held out data. But if you did all these other ways, you could form a probability distribution in a lot of the ways similar to you know, what Fisher was doing and stuff like that. You could get a whole distribution of predictive accuracy, and you could see, you know, the one way of splitting that I did, where does it fall in that? Was it like a major outlier, or, you know, things like that? That wouldn't actually be very difficult at all to do, and yet data mining people typically don't bother to do anything like that. And moreover, typically avoid talking about probability or uncertainty at all. Now, that's not 100% true. There's sort of a branch of data mining and supervised learning that at least pays some lip service to probability. It was not well represented in the books and stuff that we were using for the QMSS class last semester, but suffice it to say, it's a very minority group of supervised learning people who sort of think of themselves as Bayesian, but aren't quite as systematic as sort of Bayesian statisticians about keeping track of all the forms of uncertainty that go into a quantitative modeling exercise. But again, there could be, it's ignored, but there could be sort of the idea of probability and randomization at the heart of this, based on how you split up the big data set into two mutually exclusive pieces. And so these ways of thinking about approaches to quantitative methods can be, organized by, thinking about, okay, where does randomness and probability come in, and who's responsible for bringing it in. There's one more that I mentioned. I don't even really understand it, but in the 1930s, same Fisher came up with yet another alternative to Bayesianism. So Thomas Bayes, the person with, that is where the word Bayesian comes from, didn't actually refer to what he was doing as Bayesianism, in part because he was already dead before anybody figured out what he was onto. And his friend, a guy named Price, who was like, organizing his stuff, found this paper and then realized that it had to be sent to a journal and whatever. So Bayes didn't call his discovery or whatever Bayesianism. What is sort of associated with Bayesianism today is actually more attributable to a mathematician named Laplace, who came a little bit after Bayes, but was in France and didn't hear about Bayes's paper. He sort of worked it all out mathematically, but for some reason didn't really have a whole lot of conviction into what he had, derived. Nevertheless, Fisher heard about this approach to quantitative methods that Laplace had worked out, and he, at the time, and they knew it was sort of originally part of it proposed by this guy Thomas Bayes, and so he referred to it as Bayesianism. And like 95% of the words uttered by Fisher, it was intended to be derogatory. And so he kept coming up with these alternative ways of doing, quantitative methods in order to stop, the world from going down the path that Laplace had laid out. And so, he came up with frequentism. And just to make sure that Bayesianism would be like fully dead, he came up with yet another incompatible way of doing inference with quantitative methods and stuff to sort of show that, you don't have to be Bayesian. And this was attempted to answer questions. I don't think this one would have actually worked, but something like what could be said about where the S&P 500 will be according to some like law of stock market movement without utilizing what anybody, you or me or anybody else believed to be the case about your prediction about the S&P 500 as of January. And as a number of people, Bayesians and non-Bayesians alike, pointed out that Fisher's derivation of this, which wasn't really a derivation, he just sort of pointed to a lot of examples and was like, yeah, this could work, made no sense, particularly in the case where you're talking about models that have multiple parameters. And I don't think Fisher ever really admitted what was obvious to everyone else, that he was wrong. But, eventually, like in 1960 or something, he finally shut up about but this stuff. But like since 2000, some people have attempted to revive this idea of fiducial inference with a different justification than the one Fisher gave. I put a link to a review paper. It recently came out in JASA about this. And I don't get it. I don't really get why you would want to do this, even if it's possible. But I do know that if you want to do this in the generality that these people are talking about, and there's, you know, literally a 2-digit number of people who are pushing this, you would need something like Stan to do it correctly. And from my experience, I doubt it would turn out well. But it was intended originally, and maybe still is, as a way of sort of avoiding the subjectivity that people associate with Bayesian inference, and that we have this way of updating beliefs, but everyone could come into it with different beliefs. And if you apply these updating mechanisms, it's not the case that everybody magically converges to believing the same thing. You get maybe a little bit closer ideally, but you still, you know, each person can believe something different about the same data generating process, like the S&P 500, even upon seeing, you know, the same evidence about the, you know, quarterly GDP rate or something for the next few quarters. So what are some of the advantages and disadvantages of Bayesian inference? Well, one of the things that I think is a big advantage is its generality. A lot of people come to me and are like, I want to apply for this job, and it says I need to learn these, like, or know these 10 different things in order to work there. Can you, like, teach me those? And that's usually a lie. You don't really need to know those 10 things in order to work there. And even if it is true, you probably don't want to. But they're like, can you teach me 10 or 9 out of the 10 things that I don't know, these specific things that I need to apply for this job? Or, you know, other people, you know, come and be like, well, you know, I have to write this conference paper. I don't really know how to do it. Can you teach me what I need to know in order to, like, get through this one task that's, you know, coming up on the calendar? Or the sort of general thing like, can you teach me what's hot these days? And, you know, I can, but I don't really want to, because I don't really think that's what you as students should be doing or what's most useful. What students should be learning, whether they know it or not, learn what's general. And that will give you the biggest opportunity that you can apply that general thing to whatever situations you're facing in the future. And so Bayesian inference is the most general thing that I know of, and it remains useful in the situations, or most of the situations, in which these other forms of doing quantitative methods are specialized and originally intended to work in this sort of narrow area. So if you want to do an experiment and you have a randomized treatment, you know, that's fine or whatever. You can still apply the Bayesian approach to this. What do you believe about the average treatment effect before seeing the data? How does that change after seeing the data? And so Bayesian and experiments go together real well. You don't have to just use what Fisher proposed in the 1920s, even when you're doing an experiment. If you really do care about the sampling properties of some you know, sampling scheme that actually is going to be done over and over and over again, like the current population survey or something like that in the United States that happens every month. If you're one of the few people who should care about that, well, Bayesian estimation works really well in those cases and actually is a good frequentist estimator. So if you get the data this month and do the Bayesian thing, and get the data next month, do the Bayesian thing, keep doing that over and over again for like every month for many years, and analyze the distribution of your estimates, that's basically going to work just as good, maybe even better than doing that thing every month and applying some frequentist estimator to it. So they have essentially equivalent properties. If you really only care about predictions of observables, you don't care at all about the parameters, you might be tempted to go the supervised learning route. But Bayesian inference generates predictions as well. And moreover, it generates a distribution of predictions. And so when we did stuff last semester, you have some observations in your testing data, you get one prediction for each of those points. And then you might average over them or something like that. With the Bayesian approach, for each held out data point, if you hold them out in testing, you're going to get a whole probability distribution for each of those observations. So if some observations are particularly important, you can say, there's an 80% chance that our prediction is going to be positive, or whatever it is for that individual. And so you can really get down to making rigorous inferences about particular observations rather than averaging over the whole set. And that is extraordinarily important in things like marketing, which is more and more being driven into this sort of like personalized sales pitches that come at you from the internet, maybe without you realizing it. Fiducial inference, I don't know. But the others of them, Bayesian inference works pretty well. And moreover, Bayesian inference works pretty well, or extremely well, in the situation in which it was originally designed to deal with, which is the situation in which you want to make a decision or take some action as a result of doing your quantitative analysis. And you might ask yourself a question, well, when do you not want to take an action or make some decision as a result of doing a quantitative analysis? When are you just doing the analysis like for fun, and you're not going to like make a conclusion or do anything different regardless of how the results come out? And so Bayesian inference linked with decision theory is extremely useful when the analysis is useful, whereas other paradigms, not so much. Disadvantages: Bayesian inference is orders of magnitude more difficult for your computer to do. And that's because it's attempting to answer a more ambitious question. What should the distribution of your beliefs be? What should your uncertainty about all these things be? As opposed to just coming up with like one number for an answer and being like, okay, let's go with it, without attempting to do any quantification of what the uncertainty is. Also, I guess you would call this a disadvantage. The Bayesian approach is better suited for convincing yourself of something, to make sure that your beliefs are coherent and they're consistent with whatever data you have available. It's less useful for convincing other people who may have come in with a radically different set of beliefs than you, even if you and that person are looking at the same data. And so this can be a problem when attempting to publish, some of your results or whatever. Your reviewers may not be coming into it with similar enough beliefs that you had in order to really accept your conclusions. But that's really more of an issue with getting stuff published than it is with being correct and coherent and things like that. So just to wrap it up a little bit, the main historical issue with the Bayesian thing hinges on this idea of objectivity and subjectivity. So it's not particularly controversial that Bayesian inference is the objective way to update your beliefs in light of about anything, parameters, theta, in light of new data. However, the Bayesian idea doesn't put any restrictions on what beliefs you come in initially with. And those can be like totally irrational. And there's really nothing that Bayesian can say is, your initial beliefs are wrong. It just say, here's your wrong initial beliefs. Here's how you objectively should update them in light of these new data. But for that reason, the Bayesian approach is labeled as subjective, and because it basically varies from one person to the next. But what I think is the big problem is not that people are coming in believing ridiculous things now. it's if they have ridiculous beliefs now, like, you know, the moon is made of Greek cheese, or, you know, something like that, it's because their whole life they weren't using Bayes' rule to update their beliefs. They just sort of started, you know, believing one thing and kept with it. And unfortunately, those of you who are in psychology or, you know, political science, maybe some other things, probably encountered the fact that if you take someone who has ridiculous beliefs and you show them some data that, you know, refudiates their beliefs, they actually believe the ridiculous stuff even harder. There's some sort of problem with evolution. And so the Bayesian thing is not really a way of a good way of describing how people actually behave. People in some situations behave somewhat Bayesian-ish without going through like the formal calculations of things like they should. And, you know, it varies from one person to the next, etc. There's another branch of Bayesian stuff. It's really the same thing used in more game theory and formal modeling, you know, predicting how someone who's Bayesian would behave and react. We aren't really going to get into that, but that's more of like a modeling technique than really a description of reality. But we want to use Bayesian methods to do estimation and to show how it relates to the, I guess, broader Bayesian philosophy of doing science, particularly social science, with quantitative methods. As hopefully you've gotten the impression already, has a lot to do with manipulating and specifying and updating probability distributions. And that's going to be the hardest part. But that's where we're going to jump in, you know, and hit the ground running on Thursday. So I hope as many of you possible come back for that. If you're not enrolled, enroll. If there's other people who you think might be interested but couldn't get SSOL to cooperate, tell them to try again, or at least to show up, and we'll get all the registration stuff figured out eventually, hopefully by May. All right, that's it for today. And